Okay. Can you go away now, projection? Thank you. All right. So, I am now officially ready. Kristen, I saw you were ready right from the time I said I was going to do this, so let's start with you. Sure. So 22 says, 2 toy racetracks form concentric circles. Do we know what concentric circles are? That's probably an important place to start. So from geometry, and I know that was a couple years ago, concentric circles are 2 circles that like share the same center. So like this-ish. I tried to get them so that one is in the middle of the other. That's pretty close though. So you have 2 circles that look like this. There was one's right inside of the other. Everybody okay with that? Okay, it says each racetrack is divided into 15 identical sections. So I'm just going to draw one of those 15 sections because I know that my art skills are such that, well, it's not going to be real great. But the key there for the 15 sections is that this angle, the central angle that's formed, I know is going to be either 360 divided by 15, or I could write it as 2 pi divided by 15. It doesn't really matter which one of the two you choose. For my purposes, I'm going to use the one that's in radians, because the arc length formulas that I'm going to need to apply are a little bit simpler when I have an angle measured in radians. Is everybody okay there? But you could have done it in degrees. It's not significantly more difficult. It just gets a little messier. Okay, it says the inside car travels 1.2 centimeters less than the outer car on each piece of track. So I'm going to call this piece S1, this piece S2. I'm going to call that radius R1 and that radius R2. So I know that S1 is equal to S2 minus 1.2, right? Because it says the first car travels 1.2 centimeters less than the second car for each section. All right. It says how much bigger is the radius of the outside track compared to the inside track? It says set up 2 equations using the arc length formula and use substitution to solve. Okay. So I know that S1 is equal to R1 times theta, and S2 is equal to R2 times theta. That's my system. Everybody okay there? Notice it's the same theta in each of these equations because it's the same central angle that's intercepting each of these 2 circles. Everybody's okay with that? And now I could plug in 2 pi over 15 right now for theta if I wanted to. I'm going to just hold off on that because I have some more algebra to do to kind of get this to a place where I can do something with it. But until I do that, I'm just going to leave it as theta because it's less to write down. But you can plug that in whenever you need it to. Everybody so far so good? Okay, so I'm going to start by making the substitution for S1 that says S1 is equal to S2 minus 1.2. Everybody okay there? And then I'm going to add the 1.2 to both sides. So here's my system. There's my system. So I'm going to have S2 is equal to R1 theta plus 1.2. And then S2 is equal to R2 theta. Everybody's so far so good? And now, because both of these 2 equations are equal to S2, I can set them equal to one another, or the right-hand side's equal to one another. Everybody's okay there? So I'm looking for, in this problem, again, it's asking how much bigger is the radius of the outside track compared to the inside track. So really what I'm interested in is what is R2 minus R1, right? That's what the question is asking for. So I'm going to subtract the R1 theta to the other side. And then I'm going to factor that theta off. And then divide both sides by the theta. So when I plug this in for theta, I have 1.2 divided by 2 pi over 15. And that's the same thing as dividing by a fraction is the same thing as multiplying by its reciprocal. And so when I type that into my calculator, I get about 2.86. And I think the unit here we're using was centimeters, right? Yeah, 1.2 centimeters less. So we're measuring everything in centimeters. Kristen, how's that? You're welcome. This was probably the hardest problem in the homework set, like all the way to the end, hardest problem, because it required a little bit of creativity here, specifically realizing that this is really what you're solving for. Because even if you tried to solve the system, it's like I still have two variables in here. What am I going to do? I have R1 and R2. I can't solve for each of them independently. You're right, you can't. We don't have enough information to do that, but that's okay. Because it wasn't asking for what was the value for R2 and the value for R1. It's asking you for the difference between them, which we could solve for. But that's kind of sneaky, right? Josh. So I would say that you can certainly turn that into a decimal. Since the original piece is a decimal, I think it's perfectly appropriate that the next answer is a decimal. If I had given you like 90 degrees, I would expect that to come back as a fraction of pi, because it's not a decimal. But if you're given a degree that's a decimal, giving me back a radian that's a decimal is certainly appropriate. No, no, I don't have it. Can you tell me your name? Jason, thank you. Stuart. 24, happily. So 24 says a circular saw has a diameter of 8.25 inches. And there are 12 teeth per inch on the cutting blade. It says if the saw spins at 3,500 revolutions per minute, how many cutting teeth cross the surface each second? So basically what I want is to convert revolutions per minute into teeth per second. That's going to be my goal. So I'm just going to treat this kind of like a unit conversions problem. So I have 3,500 revolutions over 1 minute. I'll start by just converting minutes into seconds. So I know 1 minute is 60 seconds. And now I eventually have to convert revolutions into teeth, right? Well, we have one conversion factor already that relates teeth to linear distance, right? Teeth per inches. So my goal then is going to be to convert revolutions into some linear distance. And the way I do that, I remember that 1 revolution is equal to 1 circumference. So in this case, that is 8.25 pi inches per 1 revolution. Is that okay, Jason? So I'll do that for my next conversion factor. So I have 1 revolution is 8.25 pi. Again, the circumference formula there is 2 pi r, or pi times d. I just did the pi times d version since I was given the diameter. Okay. And those are inches. And that's nice because my next conversion factor, I know that 1 inch has 12 teeth. And if I go and look now at my units, minutes have canceled and I'm in seconds. Revolutions cancel, inches cancel, and I'm left with just teeth per second. So this should be the unit that I'm looking for, or the answer that I'm looking for. So all I need to do is to type this into my calculator. And you could do this like on the main screen of your calculator, or you could do it like with the fraction command. And I think that that's often going to be helpful because you don't have to worry so much about parentheses or anything. So if you do the alpha y equals, and you pick the numerator over denominator option, that'll give you the fraction in your calculator. So I can just put the stuff in the numerator together. And I'm going to skip the ones because obviously those don't matter, right? So this stuff in the numerator, 3,500 times 8.25 pi times 12. And the denominator, I guess all I have is the 60. So if I do that, I have 18,142.7. teeth per second. And since this is a rate, I guess I won't worry about like rounding that to the nearest whole tooth or whatever. Since it's a rate, I think it's reasonable to have a decimal there. Does that feel okay, Jason? Who's next? Haley. 19? Sure. So we have another one with 2 concentric circles. So I'll generate my picture here. What's going on here, picture? There we go. Let's make these actually a little bigger. If I got to draw and labels parts of them, which I think we do. That looks pretty close to me putting them concentric. It says 2 concentric circles are cut by the same angle. Okay. Well, let's draw in that angle then. Whoop. Whoop. The radius of the smaller circle is 4.1. So we'll call this, we'll label that radius as R1. And the cut arc measures 5.2. So I'll call that S1. That's 5.2 inches. It says the radius of the larger circle, I'm going to call that R2, is equal to 5.2. And it asks what is the length of the arc cut in the larger circle. So far, so good? Okay. So the key observation here that we're going to make is that the theta is the same theta in both of these instances, right? The angle that's involved, that's making each one of these 2 arcs, is the same angle. So what I'm going to do is I'm going to take this situation, the smaller triangle, or the smaller sector, and use it to solve for theta. And then I can use that answer for theta to solve for the arc length in the bigger sector. Haley, how's that feel? Good. So I think we get about 6.3 inches. Did it say, oh, wanted it to the nearest hundredth, sorry. 629. Which should be what was on the answer key, I hope, right? Okay. If anybody catches me making mistakes, please holler at me. I don't ever do it on purpose, but, you know, like we all make mistakes. Nobody's perfect yet. Maybe tomorrow. I'm working hard at it. Nobody thinks that's a funny joke. That's okay. Maybe tomorrow it'll be funny. It'll be Saturday, so better chance of you laughing about it Saturday than it is in class, huh? Anyways, anyone else? Again, happy to do more. There's no limit here. Kirsten? Sure. Do you want to just do one of these for practice? Okay. How about we do 31? Does that sound okay? Whoa. At least it wasn't in your tablet, right? Okay. So if we're asking to find an exact value, what that means is I'm either going to be using a 30, 60, 90 triangle or a 45, 45, 90 triangle, because there's no other angle measures I can find an exact value with, or exact value for, unless I'm just given more information than what I have. If all I have is the angle measure, it's got to be one of those situations. So unfortunately, we've represented this angle in radians, and probably most of us don't look at this and know the angle, the equivalent degree measure that goes along with it to know if it's a 30, 60, 45, something else degree angle. So that's what I'm going to start by doing, is just converting this into degrees. So to convert a radian measure to degrees, I multiply by 180 over pi. And when I do that, I get 30 degrees. So sine of pi over 6 is the same thing as sine of 30 degrees. So far, so good? Okay. So now I'm going to draw my 30, 60, 90 triangle. So the side lengths are x for the short side, x root of 3 for the medium side, and 2x for the longer side. So sine is opposite over hypotenuse, which reduces down to just 1/2. You're welcome. So the key is just trying to rewrite it as a 30, 60, 90, or 30, 60, or 45 degree angle, and then apply the corresponding special right triangle to it. You're welcome. But in order to do that, again, we got to remember that what these special right triangles are, right? You need the definitions for those, which I think we wrote them down in the notes last time. I was pretty sure we did that. If not, they're easy to Google, right? You'll get the answer straight away. Okay, who else? Okay, so I'm going to move on then. We can always come back and deal with more questions later if they come up. But I'm going to close out here chapter 2 today by finishing up here section 2.4. So just to refresh kind of what we did yesterday or last time, because we did a lot last time, right? We covered a lot of things. So we said that we had we talked about the right triangle definition for sine, cosine, etc. Now that was fine, but it was rather limiting because we can only take sine, cosine, and tangent of angles between 0 and 90 degrees using that definition. And we wanted to extend this so that we can deal with angles of any size we'd like. We then defined what this angle of rotation idea, which allows us to conceive of an angle of any measure. You can have all the way from negative infinity to positive infinity. So any angle size you want, we can now represent that angle by embedding it in the xy axis, fixing one side on the positive x-axis, and then rotating either clockwise or counterclockwise around the origin. And no matter what size angle you pick, whether it's positive or negative, as big as you want or as small as you want, we can draw an angle measure and define that that way. What we did then is we combined these two ideas to define sine, cosine, and tangent, etc., as a point on the terminal side of an angle of rotation. So the way we did that, so we had like our initial side here, and then maybe this is our terminal side over here. We picked any point on that terminal side, and we made a right triangle by drawing a perpendicular line back down to the x-axis, which makes this side like negative x. Why is it negative x here? Perfect, because we're in the second quadrant. It's on the left side of the x-axis. That's where the negative values on the x-axis live. And this is why, and this side we called r, which was just using the Pythagorean Theorem, the square root of x squared plus y squared. So this allowed us now to define sine, cosine, and tangent on an angle of rotation using our right triangle definition. So I said like sine of theta is now going to be opposite, which is the y-coordinate, over hypotenuse, which was the distance from that point that we chose on the terminal side back to the origin. And similarly, we said that cosine, adjacent over hypotenuse, tangent was opposite over adjacent. And then if we continue doing this for the other ones, cosecant was hypotenuse over opposite. Secant was hypotenuse over adjacent. And cotangent was adjacent over opposite. Right? And this is about where we left yesterday. Everybody kind of remember that? Okay. What we're going to do now, today, is we're going to do a little bit more with this. So it's nice that we would have the freedom to choose P to be any point, but we can make life a little bit easier for us if we fix the radius or the distance between P and the origin every time. So if we fix the length of R to be 1, what's going to happen? What shape do we form if we talk about the points that are all a fixed distance from another? It's a circle, right? So this is going to create, okay. So the possible locations of P lie on a circle centered at the origin with radius 1. So far, so good? Let's do this first. That's way bigger than I wanted it. Okay, that's about right. Try to put that close as I can to the center. How's that look to you guys? Did I get that centered pretty good? Can you tell if it's not? Does it need to be adjusted anywhere? Looks okay? What? Pretty good? Okay. Good enough for what we're going to do. Anyways, it doesn't have to be a masterpiece of art. So my locations for P now are going to always be somewhere on this circle, right? Do this real quick. Okay. So what I want to do now is I want to create some shortcuts for myself. So these angle measures that we can compute an exact value for, I would like to write them down in a compact way so that I can reference this tool later and not have to construct these special right triangles over and over and over again. Is everybody okay with that idea? Because, for example, if I wanted to do, say, like the cosine of 150 degrees, oops. Well, what would I do? I'd have to start by drawing my 150 degree angle. So here's my initial side. I go 90 and then 60 more. Puts my terminal side over here. So that's 90 degrees. That's 60 more. Do you guys agree with that? I'll pick a point then on my terminal side and make my right triangle by drawing back to the x-axis. Okay, there. Worth noting, this angle here is 30 degrees. So this makes us have a 30, 60, 90 triangle. Everybody okay with that? So using my definition for a 30, 60, 90 triangle, that side is x. This side is negative x root 3. Again, we're in the second quadrant, so the x-coordinate is negative. And then the hypotenuse is 2x. Everybody okay there? Elizabeth. So the definition for a 30, 60, 90 triangle is always this. The negative sign comes because we're in the second quadrant. So that part of the x-axis is the negative end of it. Is that okay? Now, I'm going to erase this here. If the radius is 1, that implies to us 2x should equal 1, right? Everybody agree with that? Or in other words, x is 1/2. So really this side is 1, 1/2, and then negative square root 3 over 2. Is everybody okay there? So cosine of 150 is adjacent over hypotenuse, or just this negative square root 3 over 2. Are we okay there? So that would tell me this point has the x-coordinate negative square root 3 over 2. What would its y-coordinate be? It would be 1/2, right? We went left negative square root 3 over 2, and we went up 1/2. Is everybody okay with that? Observe that this is also the value of sine of 150, because sine of 150 would be inside this right triangle opposite over hypotenuse. Is everybody okay there? So what are we noticing that fixing the radius to 1 does? That point, xy, the x-coordinate is the same as cosine of theta, and the y-coordinate is the same as sine of theta. Did you guys see that with this little example we did? So what we're going to do with this drawing that I've made here is we're going to do this for every angle that we can find an exact value for. Okay with that? So every angle that forms a 30, 60, or 90-degree angle, when we draw a vertical line or a perpendicular line back to the x-axis. Everybody okay with that idea? Hi. Good morning. Okay. So I'm going to draw this picture here. You can draw this as well and follow along with me. I'll give you a printout of the same thing. I'll put one in the content library on OneNote. So if you start drawing this and get frustrated because gets sloppy or whatever, like you have a hard time reading what I'm writing, that's okay. I'll have a very neat printout on the content library here. Probably before we leave, I'll get it in there. Okay, so just as a fair warning. Okay, so my first angle that we're going to look at, well, let's first label these points here. So this point on the right would be the point what? What's the radius of this circle? 1, so this point is 1, 0. Everybody's okay there. This point is when we have 0 degrees or 0 radians. This point here would be what? What would the coordinates be? 0, 1. Everybody's okay there? This is 90 degrees, or pi over 2 radians. And the point to the left is -1, 0. Good. So this is 180 degrees, or pi radians. And the point at the bottom is 0, -1, which is 270 degrees, or 3 pi over 2 radians. Everybody so far so good. I'm going to now label the 30, 60, and 40, 30, 45, and 9. Try one more time. The 30, 45, and 60 degree angles that would be in the first quadrant. So 30 degrees are pi over 6, 45 degrees are pi over 4, and 60 degrees are pi over 3. So if I use my special right triangle, for 30 degrees, cosine is the square root of 3 over 2. And sine is opposite over hypotenuse, so 1/2. Everybody's okay with that? Now let's do the 60 degree angle, since we have the 30, 60, 90 triangle still here, sitting here. So here, cosine is going to be 1/2, and sine is going to be square root 3 over 2. Is everybody okay there? And for our 45, 45, 90 triangle, both sine and cosine are going to be the square root of 2 over 2. Is everybody okay there? Kristen? Of course. No problem. Josh? Well, I rationalized the denominator. It'd be like 1 over the square root of 2, right? Like opposite over hypotenuse is this, but then like I rationalized the denominator. Is that cool? Okay. Good question. Again, if you're not sure on where something came from, you can always stop and ask. Sometimes I assume that we notice things that maybe we don't notice, and that's okay. It's important for you guys to, if something's going on and you're like, I don't know what you just did, or that didn't make sense to me, or whatever, to speak up. I'm happy to stop and slow down and re-explain things and try to do a better job. Okay? Let's now do those same 3 angles in quadrant 2. So if I wanted to draw the angle that makes a 30 degree with the x-axis, that's actually a 150 degree angle, right? Does everybody agree with that? That's the same thing as 5 pi over 6. But it's going to be the same values as over here, except for the x-coordinate needs to be negative because we're in the second quadrant. If I make a 45-degree angle with the x-axis, that's really the same thing as a 135-degree angle. If I convert that to radians, that's 3 pi over 4. And again, it's going to have the same xy coordinates as the 45, except because we're in the second quadrant, the x-coordinate is negative. And then if I make a 60-degree angle with the x-axis, that's the same thing as a 120-degree angle, or 2 pi over 3. And again, will be the same as that coordinate, except the x-coordinate should be negative. Is everybody okay here? Is this okay? We're going to now repeat this 2 more times in the third quadrant and fourth quadrant. But notice the only thing that's changing with our coordinates is the sign, right? So if I make a 30-degree angle with the x-axis, that's going to be like this guy here at 210 degrees, which is the same thing as 7 pi over 6. Which again is going to be the same as the 30-degree angle, except both the x and the y should be negative because we're in the third quadrant. And then the 45-degree angle is the same as 225 degrees, which in radians is 5 pi over 4. And again, going to be the same as the 45-degree angle, but both x and y coordinates should be negative. And then the 60-degree angle is 240, which is 4 pi over 3 radians, and will be the same as the 60-degree angle, except both coordinates should be negative. Everybody so far so good? Okay, we'll do it one more time. The angle that makes a 30-degree with the x-axis is over here at 330, which is the same thing as 11 pi over 6. And is going to be the same as this coordinate, except the y coordinate is negative because we're in the fourth quadrant. And then my 45 would be 315. Which is the same thing as 7 pi over 4. So it's going to be this coordinate, except the y should be negative. And then my last one here, the 60-degree equivalent is the same as 300 degrees, which is 5 pi over 3 in radians, and will be the same as this coordinate, except the y is negative. So what this drawing represents is a way to find all of the angle, or the sine, cosine, tangent, cotangent, secant, cosecant, etc., that I can for angles that have an exact value. Okay? I have an easily calculable exact value. So I don't have to go back and redraw a reference triangle and do the 30, 60, 90 or 45, 45, 90, I can just look at this because I've already kind of done the work for it. So for example, let's say I wanted to do sine of 120 degrees. So I'm going to locate 120 degrees on my unit circle, right there. And I remember that sine is the y-coordinate. So it's going to just be, is going to be the square root of 3 over 2. Krista. Of course. What if I wanted to do tangent of 5 pi over 4? Well, I'm going to locate 5 pi over 4 on my unit circle. It's right here. And I remember that tangent is y over x, or you guys remember that from yesterday? We wrote that down at the beginning of class. So the y in this case is square root 2 over 2, and the x is negative square root 2 over 2. So that just reduces down to negative 1. Is everybody okay there? What if I wanted to do cosecant of 390 degrees? Now you might say, whoa, hold the phone here, Mr. Kulak, 390 degrees is not on this unit circle. You're right, but 390 is coterminal to 30 degrees. So I remember that cosecant is r over y, or in this case, 1 over 1/2, or just 2. So all this unit circle is just a way to me to calculate these sine, cosines, and tangents that have exact values without having to go through the work of like drawing the angle on the xy axis, drawing that line back down to the x-axis, building my 30, 60, 90 or 45, 45, 90 triangle, and then doing opposite over adjacent or whatever I need to do. It's just a shortcut. That's all this is representing, is the same work that we could do by hand, but we're just going to write it all down in one place so we can just look it up. Is that okay? Couple of observations here before we move on. So note that if we're in the first quadrant, both x and y coordinates are positive, right? In the second quadrant, the x coordinate's negative, but the y coordinate's positive. In the third quadrant, we have both negative. And in the fourth quadrant, the y is negative. Remember that the x-coordinate is equivalent to cosine. The y-coordinate is equivalent to sine. And the y over x is equivalent to tangent. So in the first quadrant, all three of these are positive. In the second quadrant, which ones are going to be positive from sine, cosine, and tangent? So only the y-coordinate is positive, so only sine would be positive, right? How about in the third quadrant, between sine, cosine, and tangent, which one is positive? Just tangent. Everybody's okay there? And in the fourth quadrant, which ones are positive? Just cosine. So this is often helpful for doing the next sort of set of problems. The way that I remember the acronym for this is all silly turtles crawl. I don't know why that made any sense at all, but that was the acronym that I learned when I was in high school to help remember that. You're welcome to make up your own acronym if you prefer something else, but so this becomes quite helpful when doing problems like the following. Oops. So here we're asked to find the value of sine theta if cosine theta is equal to 5/7 and cotangent theta is less than 0. So to do this problem, I'm going to draw a right triangle on the xy axis somewhere. The trick is figuring out which quadrant that xy or that triangle needs to go in. Oops. So if cosine here is positive, what two quadrants is cosine positive in? 1 and 4. Since cosine is equivalent to x, the x coordinate is positive in the first and fourth quadrants. Cotangent less than 0. Remember, cotangent is just the reciprocal of tangent. So wherever cotangent is negative, or wherever tangent is negative, will be the same place that cotangent is negative. So what quadrants is cotangent negative in? Well, it has to be a situation where only one of x or y is negative. So that means we're looking at either quadrant 2 or quadrant 4. So which quadrant is both cosine positive and cotangent negative in? Quadrant 4, right? It's the only quadrant where we highlighted, or where the highlights overlapped. Is everybody okay with how I did that? Again, nothing super complicated about that, but it's, if you haven't seen it done, it's not always tremendously obvious how you would use that information. So I'm going to go ahead and draw my triangle, always with the perpendicular going back to the x-axis. So this is my angle theta here. So everybody, so far so good. Because I know cosine is 5/7, I know adjacent is 5 and the hypotenuse is 7. I can then use the Pythagorean theorem to find this side. So 49 minus 25 is 24. And the square root of 24 simplifies down into square root 4 times square root 6. And square root of 4 is just 2. That's how I got the 2 root 6. Is everybody okay there? You good with the subtraction going on? Where I had like 5 squared plus b squared equals 7 squared, and I subtracted the 5 squared over and square rooted. I just didn't show the work for that. But because we're in the fourth quadrant, I know that this needs to be negative, right? Everybody's okay with that reasoning. Now I have everything I need though, right? So sine theta is going to be opposite over hypotenuse. And I'm done. So we've done a lot here today. This is where we're going to stop. I want to point out one last thing that's probably I would say the most important idea going forward from this section is that if I have, like, I'm just going to write trig of theta, where trig could be sine, cosine, tangent, cosecant, secant, cotangent, doesn't matter. Of theta, where theta is some angle of rotation, like this. Is what we've done is we've shown that this is equivalent to doing, let's label this as theta. Is our right triangle definition. On this angle alpha, this one that's made between the terminal side and the x-axis. Right? That's the idea. That's the big equivalency that we built today and yesterday. That's the most important idea from this chapter. And the thing that going forward is going to be the most important thing that you're comfortable moving back and forth between is, can I take an angle of rotation, draw that on the xy axis, and create a right triangle situation that's equivalent to finding sine, cosine, and tangent of this angle of rotation. Okay? Now, when we built this unit circle earlier, that's what we did each time we did, like, found these points, is we did that process over and over and over again. We just kind of did it once and then applied it around the way, but that's all we basically did. Okay, we're stopping here. That's enough for today. You now have enough to finish the homeworks for this chapter. So I think that's like 47 to 60 is the rest of it. You'll have noticed on the content library there's a worksheet and a review sheet. Don't worry about those for the homework check on Sunday. Those will be part of the homework check for next week. I think the 60 problems is plenty of work to do for 1 week. So that's what I'll be looking for at the homework check on Sunday, is those 1 through 60 from the book. If you've started some of those other things, that's perfectly fine. No problem doing that. They are going to be in the next homework check, so you haven't wasted your time. We're still going to do them. We're still going to check them. My plan for next week is, for you guys, it would be Tuesday, the first day that we're going to meet. We're just going to take as a general work day and a review, so you can work on whatever you need to. You can ask me questions about stuff on an individual basis, but basically I'm just going to leave that whole day, that 80 minutes. Well, we'll do a homework quiz. And then the rest of that time for you guys to work on and get caught up and ask questions about whatever it is that you individually need to. So you can work on the reviews, you can work on the worksheet, you can finish up homework stuff that maybe you had questions about. But that's the plan for Tuesday. And then my plan on Thursday would be to take the Chapter 2 test. Is everybody okay with that? Seem reasonable? Okay. And I think all those dates are up on PowerSchool already. If not, I'll double check them here. Does that sound okay? Oh. Thanks, guys.